Hi, everyone, and welcome to the first remote talk of this online edition of Audio Developer Conference. Welcome to my home office in Berlin. This year, we're celebrating the 6th edition of this conference that I truly appreciate, not only because of the great content that's presented here, which is very relevant to my everyday work, but also, as Timur said before, because of the community that's formed around the event. It's exciting to see how much the community has grown since the first edition of it that focused on Jews, and how many diverse technologies for building audio applications we've embraced since. I'm really looking forward to watching all the talks on tools and languages that I don't use yet, and see if there are scenarios in which I totally should. I hope a lot of us will get inspired by approaches we've never seen before and thoughts that never crossed our minds. I hope we'll leave the conference with a lot of fresh ideas, maybe innovative, well, which gets us to the topic of the talk. I decided to call it Entry Points to Innovation, because I believe many of us wonder why we don't get to innovate as much as we'd like. We may conclude it's the technology we use, which is outdated. Maybe it's the code that's old and inflexible. Or maybe the impediments lie somewhere else. We may not be given a chance because of the hierarchies and the roles of the company. Perhaps we're impeded by our own biases, or worse, by someone else's bias. We'll ponder these and more questions throughout the talk, but before we dive into it, sorry. Sorry about that little hiccup. Well, let's go back. Before we dive through the topic, let me introduce myself first. Well, my name is Anna, and I'm a technical principal at Ableton. And for those who've never heard the company name before, Ableton builds software and hardware for music makers, the one featured in the video next to me. I joined the company to help deliver the second edition of our hardware instrument, Push. It was shown in the video before. Here, yeah. I'm actually using it right now to retrigger the playback. This is Push. Then I moved to the team that creates our instruments and effects, so-called devices. And last year, I joined a new team formed to give more attention to the integration of Cycling 74's Max with Ableton Live. And it looks like this. Max is a graphical programming environment for audio and video applications, which in the context of Ableton Live, allows you to build plugins that extend the functionality of Live. Here you can see the implementation of the LFO device that runs in Live. So now let's move on to the agenda for today. We'll start by looking at different tools for effective experimentation and discuss processes around prototyping. Then we'll look into ways of approaching large legacy code bases and overcoming challenges they entail. Then we'll see how risk management differs from risk avoidance. We'll also discuss the impact of safe testing environments on creating a culture of experimentation and bringing novelty into your projects, basically. Then we'll finally try to answer the questions, who innovates and why? So let's start with The most immediate thought that comes to mind when we think of innovation: experimenting. So what's the purpose of experimentation? Well, it is to test a hypothesis. We carry out experiments to refute or validate a thesis, a proposition. We want to be able to turn our ideas into prototypes as quickly as possible in order to ensure a quick feedback loop. This way, we reduce the risk of spending too much time with an idea that's not promising in the end, and reduce waste by avoiding polishing a foundation of a product that won't work in a desirable way anyway. So let's imagine a graph representing the relation between quality and time investment in most of the projects that we do. As we said, a prototype should require low time investment, and even if its qualities belong our acceptable standards. We want to have a proof of concept, something we can get early feedback on and feel totally fine with discarding when it fails to demonstrate potential. We can call this stage of the development process a discovery phase. So after validating our idea, we can put the prototype aside and start building an actual product. The discovery phase already gives us a pretty good understanding of what it will be like to create the real thing in the end. When we want to quickly release a version of the product that's good enough to be usable by early customers in order to get their feedback for future development, we can cut the scope planned for the final version of the product and release a so-called MVP, which stands for minimum viable product. So here we have 3 named quadrants on which we position versions of our product. So let's reiterate. Prototyping belongs to the discovery phase. MVPs lie somewhere at the intersection of the reduced scope and production ready, and the final product high up right the production ready quadrant. So what about the 4th quadrant? Well, we never want to end up here, do we? We don't want to invest a lot of time on a low quality version of the product, right? So you may think, what are the right tools for prototyping in the audio domain that save us from ending up there? Tools that enable rapid prototyping. I'd say the answer to this question is, as with most things in software development, well, it depends. It depends on who we are, what we have experience with, and what we want to do. And in order to demonstrate how different the prototyping experience may be, I was looking for a simple example to use that I could quickly implement in 3 different prototyping environments. And so I came up with the simplest sonification device I could think of. Sonify takes a video input and plays back 2 tones generated by sine wave oscillators. The first oscillator is set to the fixed value of 220 Hertz, which corresponds with the middle A in the equal tempered scale. The rate of the second one is variable and responds to the changes in the video. It produces tones between A3 and A4, so the maximum interval between the two is an octave. It's not best sounding device, rather simple, but that's not the point. The point is that it's simple, but enough to inform us about the changes in the scene with just 3 mathematical operations. So let's see it in action. little dramatic. Okay, so in order to hack this idea, we'll need to make sure first that our prototyping environment of choice will let us, first of all, to capture the camera stream, then get pixel data from the video stream, and be able to process it by applying some mathematical operations, which in our case means simply averaging the pixel RGB values and translating the dimness of the picture to an interval between the two tones, and then generate sine waves and finally play them back. So let's take a look at possible implementations of this idea in a graphical programming environment and in languages representing a higher level family and a lower level family of programming languages. So let's take a look at the implementation in Max, the graphical programming environment. All the components are available out of the box here. The pixel data can be easily extracted and passed to the objects, allowing mathematical operations on the data. We get sine wave generators for free as well out of the box. And since Max is a graphical programming environment and doesn't strictly require prior software programming skills, it eases the learning curve for those who don't necessarily have engineering backgrounds, like maybe instrument designers, UX experts, or researchers. The second prototype is written in Python. The implementation required support from some external libraries here. The Python bindings for OpenCV for capturing the camera stream, NumPy for efficient and easy processing of larger arrays of data, and PyAudio, which are Python bindings for port audio to play the tones back. And even though these don't come out of the box, the installation of the packages is very simple and possible through Python package managers. I still needed to implement the oscillators to generate the sine tones, manually spawn a separate audio thread, and manage inter-thread communication, which was quite some additional work, so that's a drawback. With Python, being a dynamically typed language with automatic memory management may not be the most favorable of choice for production-ready software, right? That needs real-time performance. At the same time, thanks to these traits, it's easy to sketch ideas in it. The ease of installing external library dependencies that we just discussed and the good documentation are definitely another advantages. So Python has always been my prototyping environment of choice because of all of these mentioned things, but most of all, because I have most experience with it and therefore feel most productive in it, which is a factor that also counts. If you want to learn more about the ins and outs of Python development, well, there will be a talk about it later today. I don't want to favor one track since it has very strong competition, and I'm glad that all the talks are getting recorded and we'll be able to catch up on them later. And finally, let's take a look at the experience of prototyping in C++ using Juice. I'll admit it was my first project fully written in Juice, and I really had to appreciate the environment created with audio development in mind. So I didn't need any external dependencies. I could rely solely on the standard modules that come with Juice. That said, I ended up having a significant lag in the video stream. And I'm probably doing something wrong, and I'm sure it's possible to fix it. But after spending quite a while figuring out, I decided not to invest more time into it since I'm just prototyping here, right? I don't really know if I will continue with this project. It didn't sound so great in the end, did it? So despite the fact that the quality of the prototype was less than desired because of this lag, I could still test my hypotheses. And that's what matters, actually. So even though I had a positive experience with Juice, the fact it requires using C++ makes it suitable mostly for professional engineers with experience in the language. So to summarize, before choosing the tools for prototyping, it's a good idea to consider the following. Am I familiar and quick in this programming language? If not, how steep is the learning curve? So again, if you're a C++ developer and know Juice, you have a fantastic tool at hand, right? But if you're an instrument designer without engineering experience, well, the learning curve may be simply too steep for you to make it the right choice. Then you can consider if you can benefit from built-in or external libraries here. And if so, are they easy to install and set up? Since, well, managing external dependencies varies vastly between environments. And if you can use higher level components like oscillators, filters, and so on out of the box, you probably don't need like deep DSP knowledge to prototype a synth, for instance, right? Then you may consider, is the language or environment or library I'm about to use well documented? Will you have to refer to the source code in order to find out how something works, or is there good documentation available? Then another important question is, will I want to share the prototype? And if so, is it easily portable? So for instance, you may consider prototyping in JavaScript. If your plan is to quickly test an idea with a big number of people, you won't be able to assist by the app setup, for instance. Then, can I easily measure and inspect my results? Well, sometimes we only want to inspect characteristics of a system and need support for quickly plotting and comparing graphs. That's when environments like MATLAB or Jupyter Notebook that integrates with Python, Julia, or C++ come handy. Well, the diverse selection of tooling makes prototyping available for non-engineers or engineers with different backgrounds. And these varied tools increase access to experimentation and broaden the group of people who get to propose ideas and communicate them through prototyping. So let's go back to our graph. Experimentation is an integral part of the development process. But please let's resist the urge to turn our prototypes into an MVP. This code is not meant to be merged with the code base, and that's why it's actually colored differently on the graph. It may save you time in the short run, but really become a maintenance burden and impede the future development of the product in the long term if you do so. And this scenario can be observed in many startups because of the nature of their environment. Many rapidly growing startups end up with scalability problems. The technical debt acquired over time makes adding new functionalities harder and slows down the whole process. There's a paper evaluating this phenomenon. The authors noticed that startups are important suppliers of innovation, new software products, and services. However, engineering the software in startups is a complex endeavor, as the startup context poses unique challenges to software engineers. Software startups are young companies aiming to build and market software-intensive products fast with little resources. And aiming to accelerate time to market, startups often opt for ad hoc engineering practices, make shortcuts in product engineering, and accumulate technical debt. So in the perfect scenario, in which our code base consists of separated, loosely coupled modules, adding new features should get faster over time, right? Since there are so many components that could be reused. I'm referring to the orange curve in the graph here. But in reality, though, we often end up with code that consists of what I like to call it merged prototypes. that are equally hard to remove as to build on top of. Which leads us to the next section on legacy code bases. So imagine we have ended up in this situation, which to be fair is a more common situation than not, that we notice that adding new features takes longer and longer, and it's hard to estimate the future work because the time it takes doesn't grow on a linear scale. What are our options? Well, let's start with the two opposite extremes. The first one, the one probably a lot of you have immediately thought of, is to rewrite everything. We start over, rethink the code design, create perfect abstractions, we achieve desired modularity. Now the code is easier to read, debug, maintain, and build on top of. Hey, we fixed the curve. Sounds great, right? So why is it hardly ever a good idea then? Well, I can speak from experience here because Ableton attempted at rewriting a big chunk of the code base. Now I'd like to put that into perspective. Ableton is not a first startup. It's a 20-year-old company with 3 main products developed in a monorepo. It consists of over 1.5 million lines of code. Ableton Live has a plethora of features, and many times even the most experienced users are not aware of some of them. So rewriting a project like that is a big undertaking. Well, long story short, the efforts got abandoned after a few years. We realized we weren't going to be able to recreate all the features our users relied on and provide them with more to guarantee a successful release. This is the risk we took. You can say we lost a lot of resources and time that could benefit our competitors, for instance, that was a big failure. But in fact, it didn't feel this way at all. Well, I saw a very positive shift in our development culture actually around that time. The way people approach the code now and think about it is different to what it was before. So what have we learned? Well, we got reminded that legacy code is code that works. By trying to redo a feature in a way that seemed cleaner and more reasonable, we were discovering that all the code that seemed unnecessary and obscure was actually important, but we were not understanding it. So rewriting features taught us a lot about our own code base, and we created a lot of documentation. It became obvious that one should never try to rewrite or refactor something they don't fully understand first. And, well, ideas that we thought were quirky, for instance, turn out to be clever once you've understood them many times. It's still not okay that they obscure the code and add up to our cognitive load, which means we spend too much brain power on unnecessary tasks like deciphering cryptic code. So adding documentation or ideally rewriting the code in a simpler way is the way to go here. Then legacy code, well, it's not good or bad. It just is. Many times when we complain about quirks in the code we don't understand, we realize we don't understand them because we're missing some context. The big code bases I work with, the mentioned 20 years old Ableton Live, the 30 years old Max, and the 10 years old Max for Live integration on top of them, have a lot of history embedded in them. The history of decision-making, the specification changing, the history of development of the C, C++, Python languages. And last but not least, no one's stoked to be rewriting an old code base full-time for a few years. So let's explore this scenario. What if we ended up in a situation in which we're at the verge of failure of our product because no one wants to maintain and develop it? Well, this scenario happened to the Plon project. Plon is a Python-based open source content management system, which usually serves as an enterprise CMS. The project started in 1999 and quickly gained popularity, forming a community of users contribute many add-on products to it. And thanks to this abundance of features and plugins available out of the box, it became a popular choice of a solution for intranets and enterprise websites. It had its prime time around years 2004, 2007. As the project was growing, it was introducing more inconsistent architectures and was becoming harder and harder to navigate and customize. So people started drifting away towards other emerging solutions, usually PHP-based, like Drupal, Joomla, or WordPress. In 2011, I joined the software house that grew on building Plon-based web solutions, but was gradually shifting towards other technologies. The last people working with Plon were the ones who'd been with the company from its early beginnings. It was actually hard for the management to persuade newcomers to get onboarded on the old framework that was hard when compared to the new offerings and clearly going towards extinction. So in 2014, Andreas Jung conducted a survey, which he revealed at the Plon conference, that revealed that the Plon community was indeed shrinking and aging because of lack of the new members. Yeah, he presented it then at that conference in a pretty direct way. So this chart that's presented here proves that the people who were members of the community still at that time were mostly the ones who joined 10 or more years before and stayed. So the maintainers of the project understood its weaknesses, but also defended its strengths. Plon was a powerful enterprise CMS solution with an acclaimed fine-grained security model with outstanding security record over the last 12 years. And since trying to get the state of the code base to a state that would make working with Plon attractive for people in the dynamically changing web world seemed pretty impossible, what they did was they blackboxed the product, meaning they let the users treat it as a closed box without needing to know anything about the details of its internals, and created a simple-to-use, clear API on top of it, which got released with, quote, cookbook-like documentation and step-by-step instructions. Alongside the main Plon API, another RESTful one emerged. Its purpose was to decouple front-end from back-end and achieve so-called headless CMS. This idea would create a bridge between Plon and any modern JavaScript framework. This solution really enabled access to a completely different community of developers by introducing new entry points to the project. So while the solution of completely blackboxing a project may seem somewhat extreme, there's a lot to learn from it. Well, let's come back to the Ableton example. The full rewrite wasn't planned at first. The initial idea was to reskin without touching the data model. We wanted to close parts of the legacy code, introduce an API on top of it, and create a new modern user interface. Yeah, maybe that could have worked. So we had this idea, right, already of introducing these APIs on top of legacy code bases that are hard to maintain. Okay. And let's see that introducing innovation when dealing with all dated systems and approaches, well, doesn't have to mean drastic revolutionary changes. Small steps taken one at a time can result in a steady evolution. And one of the most successful proponents of the technique of continuous improvement was Sir Dave Brailsford, who served as the performance director of the British cycling team. When he got appointed for the role, the team hadn't won any major cycling event in over 100 years. In fact, the performance of British riders had been so underwhelming that one of the top bike manufacturers in Europe refused to sell bikes to the team because they were afraid it would hurt sales if other professionals saw the Brits using their gear. It's quite an unfortunate situation to be in. But that quickly changed under Sir Dave's leadership. At the 208 Beijing Olympics, his team won 7 out of 10 gold medals available in track cycling, and they matched the achievement at the London Olympics 4 years later. And it was all thanks to applying the theory of marginal gains. And as Brailsford said, the whole principle came from the idea that if you broke down everything you could think of that goes into riding a bike and then improve it by 1%, you'll get a significant increase when you put them all together. So where can we look for marginal gains in legacy codebases? Well, at Ableton, while working in a particular area of code, we're encouraged to replace legacy data types with modern equivalents to increase test coverage in areas that we're touching. While adding new tests, maybe we can also cover some of the old code. Fill in the gaps in the documentation once we've understood a concept. Then we apply deprecation strategies, introduce new APIs, mark the old ones as deprecated, and then gradually move to the new one until the full replacement is completed. You can also consider developing new functionalities in a way that satisfies your quality requirements on a side and find insertion points to your code base. It's called the sprouting technique. So we've discussed ways of approaching prototyping a novel idea and of finding entry points to a code base with a lot of history. We've touched on risk involved with investing too much into an unverified hypothesis and generating waste. We've also discussed the effects of accumulating a lot of technical debt and the risk associated with both sticking with it and trying to remove it all at once. What are the other factors that can hold us back and pose the risk of impeding innovation? Well, these can be our own convictions and dogmas acquired over time. Many times, I see newcomers to the code suggesting an improvement or a new functionality and hearing, hey, you know what? Don't do it. It won't work. Or we shouldn't really touch this area. So you may ask, why are there more experienced colleagues acting as gatekeepers? Well, I assume they use their knowledge about the system to protect others and themselves as well from making mistakes, to prevent everyone from hurting the product quality. But it means that people who've spent a lot of time exposed to the depths of the code base and are convinced they know it well, start thinking dogmatically about what should be implemented and in what way. And that turns them into gatekeepers of any innovation. So dogmatic behavior and approaches serve risk avoidance. But since repeating the same patterns impedes innovation, we don't really want that, right? We don't want to avoid risk, but rather manage it. And introducing safe testing environments is an important step in that direction. They free the experts from the burden of guarding and controlling the changes to the project and open up access to it to the people free from the curse of knowledge that they have. So what contributes to the safe testing environments? Well, first of all, it's all the technical things we can rely on. Robust continuous integration systems that serve as the safety net. Good test coverage that makes it all possible. Secure sandbox environments that save us from messing up with the resources we don't want. Linters, code formatters that reduce our cognitive load. And finally, the team culture ensuring psychological safety. Knowing it's okay not to know something or to try what's likely to fail and do it regardless. So being able to rely on the technology and honesty of the teams makes risk management possible, really. Now we can plan for failure, embrace unpredictability, time-box experimentation. None of this is possible, though, without the right mindset, attitudes, and habits, which constitute a culture of experimentation. We need to ensure an environment which encourages free flow of ideas and constructive ways of articulating professional judgment. What is meant by these? By mindset can mean a set of perspectives that shape the understanding of one's own role and potential. Attitude can be described as the emotional state that creates a predisposition to perceive and solve problems in a particular way. Habits are the actions and activities that one views as crucial and valuable in exercising one's professional role, while environment is formed by the factors that shape how decisions are made and how development processes are enabled and authored. So, for instance, everyone needs to have a framework for experimentation to know when it's okay to spend their time to work on it. And there's an example from our company as well, because every 12 weeks, everyone at Ableton can spend 2 weeks of their work time developing their own ideas. But people also need to feel that their ideas are welcome and will be evaluated fairly. They need to know they will be given credit for their ideas. So without psychological safety, ideas can't flow freely. So why is the democratization of experimentation processes so important? Well, studies prove that it's the members of the underrepresented groups in a domain that come up with the most innovative ideas. At the same time, study results show that these people are not the ones that get to drive innovation in their fields. This phenomenon inspired a paper called The Diversity Innovation Paradox in Science, published in April earlier this year. The motivation for the study was to determine whether the already observed paradox holds for scientists as well. And the introduction says, by analyzing data from nearly all US PhD recipients and their dissertations across 3 decades, this paper finds demographically underrepresented students innovate at higher rates than majority students, but their novel contributions are discounted and less likely to earn them academic positions. This discounting of minorities' innovations may partly explain their underrepresentation in influential positions of academia. And since the major advancements in the audio development field have been based on successful collaborations between the industry and academia, I find this study very relevant for all of us. Also, the conclusions translate very well to our industry solely. So I'd like to leave you with more food for thought by quoting the closing paragraph of the paper. In sum, this article provides a system-level account of innovation and how it differentially affects the scientific careers of demographic groups. This account is given for all academic fields from 1982 to 2010 by following over 1 million of US students' careers and their earliest intellectual footprints. We reveal a stratified system where underrepresented groups have to innovate at higher levels to have similar levels of career likelihood. These results suggest that the scientific careers of underrepresented groups end prematurely, despite their crucial role in generating novel conceptual discoveries and innovation. Which trailblazers has science missed out on as a consequence? This question stresses the continued importance of critically evaluating and addressing biases in faculty hiring, research evaluation, and publication practices. All right. At the end of the talk, let's go back to its title. The entry points in it are supposed to indicate that it's all about access. The tools we use, the processes we define, and the environments we create determine who are the ones who get access to innovating. And we have the agency to decide who that is. So let's embrace varied technologies, introduce good APIs, sandbox our projects to ensure free and restricted experimentation, remove all the gatekeeping, and last but far from least, actively work against our own biases. But before I go, I'd like to thank a few people who helped me along the way. I'd like to thank Matthias Kneppers and Hida de Jong for setting me up with a license for video sync that they created, which is a Max for Life-based tool for extending Ableton Live with video capabilities. And it's what I've been using today. I'd also like to thank Matthias Hide and Priyanka Kodikal, Iva Karabatic, Stas Mankovic, Lilia Betz, Zofia Domorecka, and the ADC crew for all the discussions we had, feedback, moral support, and tech support you've provided me with. Thank you very much.
Thank you very much, Anna, for this wonderful talk.
Thank you.
Yeah, so that was really, really interesting. We are kind of overrunning a little bit on time, so I would suggest that we only do 1 or 2 questions, and maybe you can take the rest when you're on Remo or in Discord. So one question by Mark Mossberg. They're asking, did the whole rewrite need to be thrown away, or could any of it be salvaged?
Depends. No, as I said, we're using what we've learned from it, definitely, in many ways. So sometimes, maybe even if parts of the code base that were rewritten cannot be directly used, we still look at them sometimes when trying to implement something else. So yeah, it helps us on very many different levels, even if maybe we're not directly using that code. Yeah, I guess that's what I can say.
Thank you. And then maybe the final question by Mikołaj Piechocki. What about unit tests? There should be a way to enable refactoring with less exposure to breaking something. Shouldn't we as software developers tend to use these tests more and more just because we usually already know we will have to rewrite and refactor some parts of the code base eventually?
Absolutely. I hope you're all trying to, aiming for 100% test coverage, which, maybe, but those of you who have experience with working with old projects, or projects that have been going on for a while, know that this is usually the main problem, that the test coverage may be lacking, and adding tests for the entirety of a code base that consists of 1 million and 1.5 million lines is not so straightforward and easy. So this is what I said, that we're trying to do step by step, gradually, right? Our test coverage has improved drastically. It's only being better and better, and we are not contributing any of the new code without proper test coverage, and we have very a few levels of assuring good quality of the product at the end. Tests unit test, integration test, acceptance test, and then CI runs and so on. So yeah, I hope that answers the question.
Thank you very much.
Thank you.
Well, I don't think we have time for more questions, but you can catch Anna for the next 2 days here at ADC.
Yeah.
And yeah, Anna, thank you so much for this really, really inspiring and eye-opening talk. So thank you so much again. And yeah, I'll see you all around and enjoy the rest of ADC. Thank you so much.